Hi, AP Calculus students, Mr. Duranko here. We are going to go back to Chapter 7 and look at finding volumes of solids using integration. So this is another application of integration. And this is somewhat harder to see conceptually than the area application, but uh, we'll go slowly here and hopefully you'll be able to get it from my high quality videos. So let's say that we had to find the volume of this Hershey Kiss. That would be a difficult thing to find the volume of if it was some block. We could just do length times width times height, or if it was a cylinder, we could, apply the formula for the cylinder, but it's not. It's irregularly shaped. That's an issue, but not for calculus. What we're going to do to find the volume of this is uh, go back to these rectangles that we would stack underneath curves to find the area under a curve. And we're going to rotate that rectangle about some axis of revolution uh, and actually make this shape by rotating these rectangles around this axis. Now the volume of this solid that would get generated by revolving this rectangle around this axis would be, that's known as the volume of a cylinder, and that's the area of the cylinder, pi r squared, times the width, or the width of the disk, or the width of the rectangle. And so we can put these rectangles, revolve these rectangles around the axis of revolution, and uh, the more rectangles we put under this curve, the closer we'll get to approximating this exact shape. This only has 1, 2, 3, 4. This has 6 rectangles, but we can put an infinite number of rectangles under there and get the exact volume, so we won't have to approximate at all, and that's the power of integration. So let's get right to a problem. This is also in your book. We're asked to find the volume of the shape that you would get by rotating this curve about the x-axis. And this shape is defined by the function f of x equals square root of sine x. And we're going to put a whole bunch of rectangles inside here and then revolve them around this axis of revolution. We'll get this little Easter egg looking thing. And so that's very appropriate considering that we've just come out of Easter. So the volume, we know that the volume, as I just mentioned before, of a disk is pi r squared, the area of the circle that's formed by rotating the rectangle about the axis of revolution, times the thickness of the disk. And we can apply that now in this formula. The integral from 0 to pi, because we're going to stack these rectangles up from 0 to pi, and then it will be the area, so pi r squared, and the r will be the height that this rectangle will take. Now that will vary according to this function, so we can put this function right in there, sine of x, and that's squared, and then times dx, which is the thickness. So we have volume is equal to area times width, and we'll get, and that equation makes sense. Volume is area times width. We can move the pi out front because that's just a constant. And if we square the square root of sine x, we just get sine x. And this is dx. And so this becomes pi times, and then the integral of sine x is negative cosine x. And we want to evaluate that from 0 to pi. And if you plug pi and 0 in there and subtract, you'll find that the answer for this is 2 pi. And so this is a pretty neat application of uh, integration, and hopefully it was easy enough for you that if I gave you a couple problems where I asked you to apply this, you'd be able to figure them out. If you have any questions, don't hesitate to email me, and I'll send out an assignment momentarily. Everybody stay safe, take care, and till next time, see you later.